All right. So thank you. So we have this chart right here. I pretty much gave you a chart because these rules, you should have done all of them when you were in Algebra 1, okay? It's been like, you know, a year or two since you've seen Algebra 1, so you may have forgotten that you've done it. All right, so we have the first law is product of power. So we're basically going to go through them, okay? Look at the rule and then just an example of each one of them. So the first law we have is product of powers. And if you'll see underneath the law, I pretty much tell you what you're supposed to do, okay? So anytime you see product of powers, you're gonna multiply the coefficients and then add the exponents, okay? So I worked out the first example for you, right? So I'm trying to show you, right? So we have a power of 3, so that means I have 3 x's. Here I have a power of 5, so I have 5 x's, right? And what am I doing? I'm multiplying, okay? So the first thing, before we keep going with that, let's talk about the difference between combining like terms and using the laws of powers or power laws or the exponent properties, okay, whatever. So if I give you x to the power of 3 plus 2x to the power of 3, you know you can combine these, right? Because you're adding. So 1 plus 2 is 3x cubed. You don't touch these at all, right? All you do is add the coefficient and then bam. So that's what you do when you're adding and subtracting, okay? So what we're doing today, these are the laws when you're multiplying or dividing, okay? So for example, another example, if I give you x squared minus x cubed, can you combine those terms? No, because they're not the same base and power, right? So then you would just have negative x cubed plus x squared. You would just, that is your final answer, okay? So what we're doing today is anytime you're multiplying or dividing the same base, your exponent doesn't have to be the same. The thing that I matter, or the thing that we care about, is if the base is the same. What's my base? So if I have x to the power of n, right? This is your base, and this is your exponent. So y'all should remember that, right? So right here, product of powers, product means the answer when you multiply, right? We have x to the power of 3, and we know we're multiplying because literally they're right next to each other, right? There's no plus, there's no minus, and there's no division symbol. So the only thing left is multiplication. So x to the power of 3 times x to the power of 5, you can count here that we have 8 x's. So we really have x to the power of 8. So instead of using expansion where you're physically drawing them out every time, all you have to do is use the law of power or the product power, right? Which says that all you have to do is add your exponents, m plus n, which is 3 plus 5, which is 8. So for example, on this next one, if I were to use expansion, right, I would have 2, then I have 4 x's, 1, 2, 3, 4. And I'm multiplying, right? But because I'm multiplying variables with one number, I don't have to put a dot or a times every single time. You should know you're multiplying because they're just right next to each other, right? Then right here, we have 3x squared. So times 3 and 2 x's. So 1, 2. So if you look at what I give you, I tell you, you multiply coefficients and you add exponents, right? Well, that works because we know that 2 times 3 is just 6. And then we have 4 x's there and 2 there, so we really have 6. So x to the power of 6. And then this would be your final answer, right? And you can do the same thing just by doing what I told you. So 2 times 3 is 6, and then 4 plus 2 is the power of 6. Okay, how do you know that the product law applies? Well, product law applies if you are multiplying And you have to have multiple of the same base. The exponents can be different, right? Because all you're going to do is add your exponents, but your bases have to be the same. If they are not the same base, then you cannot add their exponents. It doesn't work that way. They're different. Okay, so next one would be quotient of powers. So quotient means that that's the result of what you get when you divide, right? So to me, quotient of powers is probably one of the easier ones because you know when you're dividing, you're going to see a fraction, right? So for the easy example, I gave you x to the power of 8 divided by x to the power of 3. Well, you can see that at the top, I gave you 8 x's because we have x to the power of 8. In the denominator, I gave you x cubed. And you can see that because there's 3 x's at the bottom. Well, anytime you have a number divided by itself, you can see that the x at the top and the x at the bottom match, right? So these got canceled out, these got canceled out, and these got canceled out. And by canceled out, I mean it's 1, right? X divided by x is 1, x divided by x is 1, x divided by x is 1. So what do we have left over? We have these x's left over. Well, how many is that? I'm multiplying x times x times x times x times x. So that means we have x to the power of 5 on the top, and at the bottom, we're left with the 1. Well, that's just x to the power of 5. Now, instead of expanding that, you could have just done 8 minus 5, which is, or I'm sorry, 8 minus 3, which is 5, instead of drawing that whole thing out. Okay, now, in high school, whenever I used to do quotient law, okay, you're gonna notice that on the second example I gave you here, you have x to the power of 3 at the top and then x to the power of 5 at the bottom, okay? So when I had quotient law, I would imagine that it was a battle, okay? So you're going to war. Who typically wins the war? Whoever has what? Who wins the war, you guys? Whoever has more. So if you have x to the power of 3 at the top and at the bottom you have x to the power of 5, who's going to win the war? The one with the power of 5 or the one with the power of 3? 5. So what does that mean? Yes, you still do top minus bottom, right? So basically whatever's left over, it's going to go to whoever won the war. Okay, so let me expand it out first so y'all can see what I mean, right? So according to what I just said, my answer should be x squared at the bottom because 5 is going to win the war. 7 over 14, remember, these are numbers, right? So you just divide. 7 divided by 14 is 1 over 2. So this is going to be my final answer. And I did that by subtracting 3 minus 5. But because 5 is bigger, that power has to go at the bottom, okay? So when we do this, we already know 7 over 14 is 1 over 2. We have 1, 2, oops, my bad. We have 1, 2, 3 at the top. And at the bottom, we have 1, 2, 3, 4, 5. Well, we can see that these cancel out, and these cancel out. So how many do we have? 2 at the bottom. So your final answer would be 1 over 2x squared. So the thing to remember here is that you're always going to do top minus bottom, right? And how do we know that we're going to use quotient law? Well, personally, to me, that's the easiest because you're going to see that division symbol. A fraction, quotient, automatically can be applied. Doesn't mean it's always going to apply, but it can be applied. Okay, next law, power of powers. Okay, so when I was in high school, I used to remember, I would always confuse product of powers and power of powers, okay? I used to always forget which one was which. So when I was simplifying a expression or a problem, whatever you want to call it, I used to always just give myself a quick example. So I would always do, okay, so what's So like, let's say I had this and I couldn't remember, I would just do the quick expansion of it. And then I would remember, okay? Or like if I did X times X, that was my go-to example right there. And I'm like, okay, so if I have that, that means I have 1, 2, 1, 2, 3. So that's 5. That means I'm gonna add. That's how I would remind myself, by the way. Okay, anyway. So product of powers, here you can see the expansion of it, right? So you have parentheses, p to the power of 5, parentheses, and then a 3. So you know that it's power of powers because you're going to have a power right next to each other, okay? And yeah, you're going to see parentheses. So power, parentheses. You have to see the parentheses and the power on the outside, okay? So if we expand it, you can see why we get what we get. So you have 3p to the power of 5. So I have 1p to the power of 5, 2p to the power of 5, and 3p to the power of 5. Then if we break that down even further, you can see that inside the parentheses, I have 5p's. So I have 5p's there, 5p's there, and then 5p's there. So then how many p's do we have? 15. So instead of drawing all of that out, if you can identify that this is power of power, you could have just done 5 times 3 is 15 and been done. Now, you're going to notice that over here in your little helpful guide, I put distribute power to every power inside parentheses. Everything inside the parentheses has a power. Everything, even if you do not see one. Okay, so for this next example, you're going to see parentheses 3pr cubed parentheses squared. I know this is power of power because I see parentheses with the power on the outside. Okay, so this is power of power. So every power on the inside has to get a power. So this base of 3 has what power if I don't see one there? What number is implied and invisible? No one knows what power is there that's invisible? What number is allowed to be invisible and still mean something? Okay, let's take it back. If I gave you X, what number is in front of that? 1. So what's the exponent? 1. So for this example, this 3 has an exponent. That exponent is 1. That P has an exponent. How many P's do I have there? 1. And that R already has an exponent. It's 3. So all you have to do is grab your exponent on the outside and you're going to multiply with every exponent on the inside, every single one, whatever is inside, I don't care, okay? So that means we're gonna have 3 to the power of 1 times 2, P to the power of 1 times 2, and then R to the power of 3 times 2. So what does that give us? That we end up with 3 squared times P squared, and then 3 times 2 is 6, so R to the power of 6. You should notice that R squared can still be simplified. So we end up with 9P squared R to the power of 6, and then this would be your final answer. You could expand, right? But that just takes too long, but we're gonna do it anyway. So we would have 2, we have 2, so 3PR cubed, that's 1. And we need another one because we have 2 sets of those parentheses. And inside these parentheses, we have 3PR to the power of 3, right? Now inside these parentheses, I can expand even more. Inside these parentheses, I have a 3, a P, and 3 R's, 1, 2, 3. And then I have that again, times 3 times P times 3 R's, 1, 2, 3. Here you can see that 3 times 3 is 9. We have 1P here and 1P there, so we have P squared. And then we have 3 R's here and 3 R's there, so we have 6 R's. So P or 9P squared R to the power of 6. That would be your simplified form. So the law here, remember, how do you know you can use this law? Because you're going to have a power on the outside that does not, that its base would be whatever's inside of the parentheses. So let's look at what we've done. Product rule. You have product rule if you have multiple bases, right? And you're multiplying. You have quotient law if you have a division symbol. And you have power of power, because think about the name, power of power, right? So you're going to have a power and a power, double power, power of power, power to the people. I don't know what to tell you. Okay. Product, you're going to have multiple bases and you just add their exponents. Power, you're going to have power, power. Okay. Now, these three rules we've already been using in the classroom, whether you knew it or not, okay? When we multiply polynomials, when we divided polynomials, when we've been using these laws already, okay? So our next three laws don't really have an expansion. They're really just something you have to memorize, okay? So we have negative power. How do I know to use negative power? You're gonna see a negative power. It's kind of like self-explanatory, okay? You have a negative power. So right here, we can see that we have a -4. Well, here I tell you, when you have a negative power, you're gonna slide to the other side. Okay, well, miss, what side? I don't know what you mean. We already know that everything can be written as a fraction, right? So this is really over 1. So if you have a negative as your exponent, you're gonna grab that base with its power and you're gonna slide to the other side. So this is going to give us, we now have x to the power of 4, and notice the negative is gone. What's at the top, miss? What number goes at the top? Okay, well, look at your original problem. This coefficient right here is just a 1, so you're gonna have a 1 there. That stays there. Okay, so if we look at the next problem or our next little mini example, you're gonna see that you have negative exponents on the numerator and the denominator, which is why I put you slide to the other side. I don't care what side you're on. If you're being a negative Nancy, you're gonna get thrown to the other side, okay? And then you're gonna be a positive person now. So you can see that this has a base of 2. I don't care what the base is. The exponent is negative. So because I have a negative exponent, that means this entire thing is going to get thrown to the other side. Well, what do we see at the denominator? We also see a negative exponent. So then that means that this entire thing is going to go to the other side. So anytime you're negative, you just throw it to the other side and the negative goes away. So what do we end up with? We end up with p to the power of 4 because my negative is gone. And at the bottom, you end up with 2 to the power of 1/2. My negatives are gone. Now, if other rules apply, you would apply them, which for this one, it so happens. Last week, we talked about our denominator. We have 2 to the power of 1/2. So this would be power of 4 and then the square root of 2. Just so that you know what that would be, okay? But that rule is going to come back again right now. But you could also leave it as 2 to the power of 1/2. It depends on your multiple choice. Okay, again, for this next problem, we have 3p to -3 times w divided by x to the power of -2. So same thing. Now, with this one, what I'm trying to accentuate is that you only move whatever has a negative power. So here we have a power of -3. Who has the power of that -3? What base? When I ask y'all a question, this is where you like type it in the chat so that we can like move on. So who has the power of the -3? What variable, what base? Or I shouldn't say variable, I should just say base. What base has the power of a -3? Good. And so because this negative, that means that only that is going to get thrown to the other side. And then you see that at the bottom, this one has a negative. So this one's going to get thrown to the other side. So our answer ends up being 3x squared w over p to the power of 3. So it does not matter where the negative is at. All you have to do is throw it to the other side and the negative goes away. Okay, which is basically what this rule is showing you. It makes it seem like it's always going to go to the bottom. It's really not. It's just going to get thrown to the other side. Okay, so if you have 1 over a to the negative m, that's just going to be a to the m on the top. Okay, so that's what I mean by it goes to the other side. You don't have to write that part down. You have it written over here, right? You just slide to the other side. Okay, 0 power. 0 power is so easy, but it's so easy to forget. I don't know why. Okay, so any base with a 0 is 1. That's it. So right here, we have x to the power of 0. And so our answer is 1. You're done. Okay. So when you look at the next example, 2 times x to the power of 0, who has the power of 0? I'm gonna start calling on y'all because y'all aren't answering me in the chat. Daniel, who has the power of 0? 2x or both? Brian, who has the power of 0? 2x or both? Anthony, who has the power of 0? The 2, the x, or both?
The x.
Okay, why do you say that?
Because it's above it.
Okay, so do y'all see 2x to the power of 0 and then the problem right next to it? What's the difference between those two? What is one of the big differences there?
Parentheses.
Parentheses, okay? So this right here, you guys, is the power of parentheses, okay? So in this situation, x is the only one that has the power of 0 because these are two separate bases, right? Okay, so that means that we have 2 times x to the power of 0 is 1. So 2 times 1 is 2. This would be your answer. Now for the next one, we have 4pyz, all of that, and I'm saying all of that because I see parentheses, all of that has the power of 0. So do we see the difference between the one we just did to this one that we're doing now? Okay, so then right here for this one, this entire thing is a power of 0. So the whole thing is equal to 1. I don't care what's on the inside because the parentheses are there, and the parentheses are telling me that all of it is going to have the power of 0. So then the answer is 1. You're done. Okay, so for the next one, who has the power of 0? X, Y, Z, or all? Daniel? Who has the power of 0 for the example we're on now? X, Y, Z, or all of them? Why? What did we just say about this example right here? 4pyz to the power of 0. What's the difference between the one we just did to the one we're doing now? So who has the power of 0 then? Just the z. So then that means the only base that has the power of 0 is this one. So we have x, y, and then that z to the power of 0 is now 1. So our answer would be x, y. So basically any base that has a power of 0 is just 1. That is the rule. That's the law. of exponents. Okay. Now for this last law, we kind of talked about last week, right? Because we were starting our radicals unit or whatever you want to call it. So rational power, basically all you do is bottoms out, okay? So the bottom, whatever is at the bottom in your denominator in that exponent is going to be the outside, which is going to be your radical, okay? The other way I explained it is I explained it as a little cowboy on top of a horse, right? Your cowboy goes inside the house, but the horse waits for you outside. So here we have 4 to the power of 1/2. So because that 2 is at the bottom, that is your horse. Your horse is going to go on the outside, right? And then the cowboy, which is a 1, goes on the inside. So we already know when we have a square root, you don't have to put that 2. That is an implied 2. And the square root of 4 is 2. So if you can simplify it, you must. So for the next one, before I can apply rational power, what law should I apply? Five, 4, 3, 2. Brian, what do you think? The example we're on now, the question that I just asked. So what law should I apply before I do rational? Those of you at home, you need to be answering or you're going to be next. So yes, I asked him, but you should also be typing me your thoughts. Thank you. Yeah, there you go. So anytime I ask a question, just go on ahead and type your answer, even if I call on someone, because I'm still going to be looking for your answers in the chat. What do you think, Danny? Yeah. Before I convert this into a radical, what should I apply? X to the power of negative 1/2. What law should I apply? So do y'all see that negative? So what law would that be? There you go. So when we have a negative exponent, what do? You just slide to the other side. So this is really 1 over x to the power of 1 over 2. Now we can use rational power, right? Look at the rule. In order to do rational power, do I want a negative? No, right? So then it would make sense for us to apply the negative law first, right? So then now that we have applied that, now whatever's at the bottom, throw out, and that's going to be my radical. So x square root of 1. So the square root of x, that would, oh, my bad, just kidding. Under 1, there we go. 1 over square root of x. Next one, we have, again, the power of parentheses. I need y'all to make sure you pay attention to the power of parentheses, okay? So the power of parentheses, here you can see that this entire thing is to the power of 3 over 4, okay? Not just the r, right? So you can see that the example right after that, the main difference between them is that one has parentheses and one doesn't, right? So you need to make sure you keep that in mind when you're simplifying these things. Because all of this is in parentheses, right? I can just go on ahead and throw this outside. So this would be the 4th root of this entire thing, which was 3r to the power of 3, right? Because my numerator was 3. So then hopefully you see that this is power of power. So our answer is actually the fourth root of 3 to the power of 3 r to the power of 3. Simplify that, 3 to the power of 3 is 27, so the fourth root of 27 r cubed. But for the next example, which by the way, that's the power of 4 over 5. I didn't realize that was so little, I'm sorry. You can see that there's no parentheses. So the 2 does not have a power of 4 over 5. It only has that power of 1. So the only thing that's going to go or that's going to get converted into a radical would be the p to the power of 4 over 5. So we're going to have 2 to the power, or not to the power, I'm sorry, times the fifth root of p to the power of 4. And then that would be your answer. It is the power of parentheses. Okay, moving on. Boop, boop, boop. Okay, so radical properties, they're pretty much as the rules above. The only difference is that I'm just explaining it with radicals, right? So you have product, which basically means that if you have the same root, right? You can put them under the same house. So because we have, so basically what I'm talking about is this right here, right? This radical symbol that I'm highlighting green. If those are the same, then you can put A times B together in the same house. And you can also separate them, okay? So you can put them together or you can separate. You can go just how you can go to the, from left to right, you can go from right to left. It goes both ways. So example, we have the cube root of 4 times the cube root of 2. Because these cube roots match, right? Then that means I can just put the entire thing under the same house. So 4 times 2. And 4 times 2 is 8. Now, that cube root of 8 can be simplified, but I'm just going to leave it like that for now to accentuate the property, okay? So basically, the cube root of 4 does not exist, and the cube root of 2 does not exist. But when you multiply this 2 and 4 together, all of a sudden it exists now, right? So this 8 is really 2 times 2 times 2. So the cube root of 8 would be 2, because 2 to the power of 3 is 8, FYI. Okay. Quotient property, same thing, but with division, right? So if you have a fraction inside of the radical, you can separate it into 2. Why is this helpful? Because sometimes either the numerator or denominator, maybe they can be, sometimes if they're separated, one of them is a perfect root of whatever you're looking for, and the other one isn't, okay? If you keep them together, it's harder, but if you keep them separated, you can simplify one over the other. So here, I don't know what number that is. I think it's an n, okay? So we're just gonna say that this would be equal to the nth root of 32 over the nth root of 2. Okay, that's all we're saying, that you can split them up. Okay, an expression is completely simplified when? Basically, as long as you can't apply any more power properties or exponent properties, then you're pretty much done. That's pretty much everything that's being said there. Okay, so we're gonna do some of the easy ones, right? Or we're just gonna do a few of these together. So example 1, what law do we see? Type it in the chat. I'm gonna give you about 10 seconds. If you don't, I'm gonna be calling out on you. 10. What law do you see? 5. Make sure you're typing it to Veronica Rios, the host, not the co-host, because that's probably why I'm not seeing some of your responses. Okay. Okay, so what we are seeing, I forget that y'all need time to look at the chart. I'm sorry. That's why I gave y'all extra time. Okay, good. Brian, what law do you see? What do you think? So we have x to the power of 4, y to the power of 2 times 4 times y to the power of 4. What do you think? Product of powers. Where am I going to apply product of powers, you guys? What am I applying product of powers to? Which base? So the rule that y'all see is product law, right? So who am I applying this product law to? What specifically, right? So which base would I be applying this product of powers? Am I applying it? What basis do I have? I have a base X, Y, 4, Y. Those are the bases I have, right? The big ones. So who am I going to apply this law to? My X's, my Y's, my 4's. What do we think? So remember, in order to apply product law, I have to see multiple of the same base, right? I already know I'm multiplying everywhere, right? X to the power 4 times y squared times 4 times y to the power of 4. So that's not the issue. The issue is, where do I see multiple of the same base? That's the only time I can apply product law. So what base do you see more of one or multiple of? Okay, so someone said X. Do you see another X anywhere there? No. So can I apply product rule to that? No. What about Y? Do I see another base of Y? Yes. I don't care if they're separated, you guys. It doesn't matter because you're multiplying, right? Remember, one of the special properties of multiplication is that it doesn't matter what order you multiply, it's the same thing. So you can multiply these two things, right? They don't have to be right next to each other. So because this is my product law, then that means I'm gonna add 2 and 4. So we're gonna have, I'm gonna pull out this 4 to the front because I like my coefficients in the front. I have x to the power of 4, and then 2 plus 4 is 6. So this would be your final answer. 4, that's the only base you have of that 4. That's the only base you have of that x, and that's the only base of y you see, right? So they have all been simplified. Example 2, what law do we see? Type it in the chat. Good, Emily. I agree. Good, Ramon. I agree. Yes, I agree, Dan. Okay, so the law here that's going to apply, because I see parentheses with an exponent outside, then I know I'm going to want to apply power of power law. So I'm just going to write power, right? What is power of power? Ah, what fell? My earring? So what is power of power? That's why I give you this chunk right here, right? I'm basically telling you what to do. Distribute power to every power inside parentheses and multiply the powers, right? So because this is power of power, all I have to do is give everything inside a power, which it doesn't yet. This X has a power, but this 3 does not. So it needs the power. And then I'm just going to multiply all these powers. So we're going to have 3 squared and then x to the power of 8. Well, 3 squared can be simplified to 9, right? And then x to the power of 8. You're done. All right, next one. Example 3. Okay, I'm gonna give y'all about 30 seconds to think about what laws y'all see. Go. Type any law you see. Type all the laws you see. Cool. So some of the things y'all saw was power. Y'all said negative. I'm just writing what you, and then quotient, which I pretty much agree with, right? I know we see power because I see parentheses with the power on the outside right here. We see negative because I see a negative exponent there, and then I see quotient. Just like the order of operations, you're not gonna do everything at once, right? You're gonna do one at a time. So if I had to pick which one of these would I do first, it's really just up to you and what makes more sense to you, right? So personally, me, I'm gonna do negative first because I like to get rid of negatives if I can, okay? So that means that this y has a power of -2, so I'm gonna slide to the other side. So now I have 3x squared, y squared, that negative is gone, over 2x, all of that to the power of 4. So negative law has been applied. Then we still see power and quotient. Now, can you do quotient if you have parentheses in the denominator? Probably not, right? That kind of makes sense. Like you're not going to want to do that, right? So obviously we're going to go on ahead and do power of power first. So that means that everything in here has to have a power. So that has a 1 and this x has a 1. So then we're going to have 3x squared, y squared at the top. And on the bottom, we're going to have 2 to the power of 4 and then x to the power of 4. So we have done our power law, right? No more parentheses. I don't see power law anymore. What you can do is you can simplify the 2/4, right? But we can do that at the same time as we do our last law. So the last one we see is quotient. Now, where can I apply quotient? To what basis? What basis can I apply quotient to? Go ahead and type that in the chat. 5, 4, 3. Yes. So we can apply it to my x's, right? Because the bases match. Remember, a big part of this is that bases have to match when you do product or quotient, right? So then remember, this kind of goes back into that whole war thing, right? If you want to look at it that way. So out of x squared and x to the power of 4, who's going to win? Top or the bottom? 2 times 2 is 4, 4 times 2. The bottom. So x squared would go to the bottom. So then your answer would be 3y squared over 16x squared. And this would be simplified. Now, the reason, so this green part right here, right? When you do 2 minus 4, I know that's -2, right? The reason it stays at the bottom is because you would have x to the -2 in your numerator. Well, either way, this is negative law, so you would slide to the other side. So you're pretty much just skipping a step, okay? By understanding that there's gonna be more x's at the bottom and you just leave it there, you're pretty much skipping the negative exponent, right? 2 minus 4 is -2. So you would have an x with a -2 at the top. But instead, we're just skipping that step and leaving that at the bottom. Okay, example 4, same thing, but your bases are numbers, right? You can still apply the laws of exponents. Why? Because these are the same base and you're multiplying them, right? So what law would this be? Product, because we have multiple bases. So we're going to have 7 to the power of 1/4 plus 1/2. That's what you do with the exponents, right? So on the side, we're going to have to do some work. So 1/4 plus 1/2. In order to add fractions, we know they have to have a common denominator. So this is 1/4 plus 2/4. All I did was multiply 1/2 by 2/2. So 2/4 is half, right? They're still equivalent. So 1 plus 2 is 3/4. So this turns into 7 to the power of 3/4. Well, now we see rational. So the bottom out. So we would have the 4th root of 7 to the power of 3. 7 to the power of 3, I don't know what that is. 7's a prime number, so 7 times 7 is 49. 49 times 7, I don't know what that is. 343. So this would be the 4th root of 343. Okay. Example 5. What laws do we see? Type them in the chat. What laws do we see for example 5? Okay. I'm gonna give you a few more seconds. Type at least one law that you see. Even if you can't identify all of them, you should be giving me at least one. Okay, so multiple of you have given me negative, power, and product. Oh, and some of you gave me rational. Okay, so here's the thing. Do I agree with negative? Yes. So let's go ahead and write that down. Oops. I agree with negative. I agree with power, right? Because we have a negative there and it's also outside of my parentheses. So I see power to the power. What I don't agree with right now is product. Why? Well, let's look at our chart. According to product rule, remember, what has to be the same? The base, right? Okay, so if I come down, back to this example, are these the same? No, I get it, they're numbers. Well, miss, I can multiply numbers. You're right, but we're doing laws of exponents, not, you know what I mean? So if you're doing laws of exponents, you have to make sure that the bases are the same. So I would not be able to add 5 plus 5, okay? So what we're gonna go on ahead and do is apply negative law. So that would be 1 over 4 to the power of 5 times 3 to the power of 5 to the power of a positive 1 over 5 now, right? And the reason that 1 is at the top, because there's a 1 out here, right? That we don't really talk about. So that's why there's a 1 at the top, right? Okay. Now we can distribute. So we've done negative. Now let's do power, okay? So this 1 over 5 times 5 is really 5 over 5, which is just 1. So we have 4 to the power of 1. And then we have 5 times 1 over 5, which is 5 over 5. So we have times 3 to the power of 1. Now that they both have just the normal whatever, we can just multiply the numbers, right? Because they're just normal numbers now. So we have 1 over 12. And then that would be your final answer. But do we understand why product rule does not apply? Okay, they have to have the same base, and these do not. Example 6, we have 5 over 5 to the power of 1 over 3. So we have a rational exponent, so that means that I can convert that into a radical. So we would have the cube root of 5. Now, we would not want to leave this like this, right? But we're gonna do that at some other time, not now. So we're gonna leave it like that. All right, next. Example 7. Again, we're just dealing with numbers, right? What laws do we see? What laws do we see? Okay, so for the most part, I keep seeing power of powers, right? And I agree because we have that. So the part we want to look at, so yes, we see power of power. So let's write that down. So we see power of power, okay? Now, remember, everything inside has to get the power of power. So that means that I'm gonna distribute this 2 to this power and to this power, right? I have 2 bases. I have a base of 42 and a base of 6. Both of them have exponents. Every base has to get that new power. So we're gonna have 42 to the power of 2 over 3 over 6 to the power of 2 over 3. Now, what law do we see? What is my exponent? My exponent is a fraction. So what law would that be? If my Remember, in order to do product and quotient, you have to have the same base. Is 42 and 6 the same base? No, right? So yes, I'm glad you thought of quotient because remember earlier I said, quotient's the easiest to identify, but it doesn't always apply. So you just have to be careful and make sure that it applies, right? So we have 42 and 6. Those are different bases, so I cannot do quotient, okay? What we can do is rational, and I can do rational because my exponents are fractions. So that means that for both of these, whatever's at the bottom goes out. So we're gonna have the cube root of 42 squared over the cube root again of 6 squared. So the other power we saw was rational, right? Now this is where you're, we can check to see, hey, is this gonna simplify or not, right? So what I like to do, instead of doing 42 squared, which would be 1,764, okay? I'm gonna check for 42 to see what factors it has, right? So I'm gonna come over here and I'm gonna do 42 first. So 42, well, what gives me 42? 2 times 21, and 21 is 3 times 7, right? But we have 2 of those. So we have another 42, and that's gonna be the same thing. 2 times 21, and 21 is 3 times 7. So these are the factors we're working with, right? 2, 3, and 7. Now, I want the cube root. So that means I want groups of 3. Do I have any groups of 3 on here? I have a 2 and a 2, 2 3s, and I have 2 7s. Do I have enough numbers to make a group of 3 anywhere? Do we have any of that? Do y'all understand what I'm saying? Do you understand what I'm asking? Do I need to rephrase it? Rephrase it? Okay. So what I'm asking for, do you see how out here in pink, I put 3, right? That cube root, that means that I'm looking for perfect 3s, not the physical number 3. I'm looking for perfect groups of 3, right? So for example, the cube root of 8 is the same as 2 times 2 times 2, right? 2 times 2 is 4, 4 times 2 is 8. So 8 is a perfect cube, right? So why? Because it's a group of 3. I don't care what number it is, as long as it's a group of 3. Here, I just broke this 42 squared in here, right? So essentially, I'm looking for this, cube root of 42 times 42. Instead of multiplying 42 and 42 together, which is 1,764, I left it like that, and I'm breaking it down separately. So 42 is 2 times 21, and 21 is 3 times 7, right? So the factors that make 42 is 2 times 3 times 7. Those 3 numbers, when I multiply them, gives me 42, right? So if I have 2 of them, then that means that 2 times 3 times 7 times 2 times 3 times 7, when I multiply those 6 numbers together, it's gonna give me 1,764. So what I'm looking for now is cube root. I want groups of 3 of the same number. Do I have any? I have 2, 2. Do I have any more 2s? So I can't take that number out. I have 3, 3. Do I have any more 3s? I can't take that number out. And I have 7, 7. Do I have any more 7s? No, I don't have enough to take anything out. It has to be twins, triplets, quadruplets, quintuplets, whatever, okay? They all have to be identical. So that means that 42 squared cannot be simplified. So I can leave this as, oops, my bad. I can leave this as the cube root of 1,764, which is 42 squared, because it doesn't have a perfect cube, okay? There's no numbers that I could take out from that. Over So then we have the cube root of 6 squared. So now we're going to do the same thing, but with the 6. So we have the cube root of 6 times 6. Do you see what I'm doing there? Instead of doing 36, right, because it's a bigger number, I'm just going to break down the smaller numbers, right? So 2 times 3 is 6. So 2 times 3 is 6. Well, what factors do I have here? Do I have enough factors to take groups of 3 out? So I have a 2 and a 2, but how many do I need? I need 3 of them. Do I have 3? No. Then I have this 3 and that 3, but I need groups of 3. So can I take any of those out? No. So then that means that my denominator is going to stay as the cube root of 36 because I cannot simplify it. So I can actually write this as the cube root of 1,764 over 36. Oh, is 1,764 divisible by? I didn't check that. 1,764 divided by 36. Oh, it is simplified. Okay. So this simplifies to the cube root of 49. 1,764 divided by 36 is 49. But 49 is still not a perfect cube, right? 49 is 7 times 7. We don't have enough 7s to take it out. So it's not a perfect cube. It's a perfect square. So if this said square root of 49, it would be 7, but it doesn't. It's cube root, so it's not 7. Okay. So this actually simplifies to that. I didn't even think to divide that last period. Okay, example 8. Okay, so for example 8, we're really just practicing simplifying, okay? So the way I do it at first, okay, is 135. What can I divide 135 by? What are factors of 135? Remember, I want to try to do prime numbers, right? So 2, 3, 5, 7, 11, 13, 17, 19. I don't know, those are the top ones out of my head. So what number can go into 135? So the first number I thought of is 5, right? Because anything that ends with a 5 or a 0 is divisible by 5. So 135 divided by 5 was 27. So 5 times 27. Well, 27 is what? 3 times 9. Can I keep going? Brian, pick your head up. What is 9? 3 times 3. So the numbers I'm looking at are the ones that don't have any branches coming out of them, right? So 5, 3, 3, and 3. Do I have enough groups of a number to take out? Yes, what number? 3. I have one group of 3 that I can take out. Does everyone see that? So this one group is going to come out, right? And whatever number is in there, that's the number you're taking out. So we're going to have 3 times the cube root, whatever is left inside, which is this 5. So 5. So cube root of 135, I'm sorry, is 3 times the cube root of 5. That is what that simplifies to. Because 27 was a perfect cube. 3 times 3 times 3 is 27. And the cube root of 27 is 3. So this would be your final answer, simplified. Okay, so 9, 10, and 11. I'm going to go on ahead and do 11 because I told 6th period to do 9 and 10 on their own. So when you submit your notes, make sure 9 and 10 is completed. So we're going to do number 11 because that's the one they wanted me to do with them. Okay, they said it looked harder. Which I don't know why, 216 and 176, that looks harder to me, but okay. They wanted me to do 11. Do y'all agree or do y'all want me? No, we'll just do 11. So it can be the same. Okay, so the difference between 9, 10, and 11 is basically that I have a 3 on the outside, but that doesn't matter. It's the same thing, okay? So for 9, you have square root, so I want groups of 2. So for every group of 2, I can take that out. For 10, I want groups of 4. So for every groups of 4 of the same thing, I can take that out. For 11, I have groups of 3, right? So variables to me are way easier than numbers. So we're going to do the number first, right? So we're going to do this 24. Can I find a cube root inside that 24? So over here on the side, cube root of 24. Well, let's break it down. 24 is 2 times 12. 12 is 2 times 6. And 6 is 2 times 3. So the numbers I'm looking at are the ones that don't have branches coming out of them, right? So 2, 2, 2, and 3. I want cube root, which means I want groups of 3. Do I have any? Do I have enough to make a group of 3? What number? 2. I have a group of 3 right here, which means I can take this out. What number is that? 2. So I'm going to take that 2 out, and I'm going to be left with the cube root of whatever's left inside, which is anything that did not have enough to make a group of whatever I'm looking for. So that 3 is going to stay in here. So what does this mean? How does this fit into what we just did? That means that on the outside, I already had a 3. Now I'm going to multiply that with the 2 that I took out, that cube root that I took out, or that perfect cube. And then on the inside, we have this 3. And then we have a to the power of 4, b squared, and then c to the power of 3. Now, we did the number, right? Which was where you have to break down your factor tree. So for variables, in my opinion, they're way easier because all you have to do is expand them out. So how many A's do we have? 1, 2, 3, 4. How many B's do we have? 1, 2. And C's, 1, 2, 3. Remember, I am looking for groups of 3. So let's start with A's. Do I have enough A's to take out a group of 3? I'm waiting for y'all's response. Do I have enough A's to take out a group of 3? Can I form? Yes. So we have one group of 3 there, which means I have an A that's going to stay behind, right? So this group of 3 is going to come out. So I'm going to take out an A. What about B's? Do I have enough B's to make a group of 3? No, there's only 2 of them. So they're going to stay inside. What about C's? Do I have enough C's to make a group of 3? Thank you. Yes, I do. I have exactly one group of 3. So I'm going to take that C out. So that means that whatever you take out goes on the outside, and whatever did not have enough to form a group stays on the inside. So we're going to have 3 times 2, we know is 6, AC, cube root of whatever got left behind, which was my 3. I had 1A, B squared, and no C's left over because I had exactly one group of C's, so there's no more C's on the inside. The cube root of C cubed is just C, so we took that C out. So then my final simplified answer would look like this. Okay. Now, rationalizing the denominator was a pain in my butt last period because y'all always get the better version of me, dang it. Y'all should be glad about that. Okay. If we have a radical in the denominator, and then we must multiply the numerator and denominator to make the denominator a perfect nth root. Okay, we did the mistake of starting with example 1, 6 period, so we're not going to make that mistake. So we're going to go straight to example 3, okay, because that's an easy example to get us started. And your homework is going to look like examples 3 and 4. So we're going to get started with those, okay? And that's probably where we're going to stop because that's where I stopped with 6 period, and I want you to be at the same spot, okay? So for example 3, we can see that we have the square root of 5/8. So we can actually break that apart, right, to the square root of 5 over the square root of 8. Okay, and that's just using that quotient radical thing, right, that I can split it up because the fraction falls under the same group. so I can just break it apart. So what I want to do, okay, square roots are the easiest. They're just so nice. They're perfect, okay? In order to rationalize the denominator, all you have to do is multiply by the denominator when you have a square root. That's it, okay? So when you have a perfect square root, so these two are the easy ones, okay? So times square root of 8 over square root of 8. Why are we multiplying by the square root of 8 over the square root of 8? Because the square root of 8 over the square root of 8 is just 1, right? So essentially, you're multiplying by 1, but you're not multiplying by 1, but you are. You know what I mean? Okay. So you're multiplying by 1. So you're not really changing the actual fraction. You're just manipulating the numbers. Okay. So what happens here is that when you multiply by that, you end up with, in the numerator, square root of 5 times square root of 8. And in the denominator, we end up with square root of 8 times square root of 8. Well, what happens there? Okay, so in the side, let me show you why this works, right? Square root of 8 is really just 8, 1 over 2 times 8, 1 over 2, right? So you have the same base, so you can just add their exponents. So you really end up with 8, 1 plus 1 is 2, which is over 2. Well, what's 2 divided by 2? 1, so you end up with 8. Okay, this is why that works. So that means that we have square root of 5 times square root of 8 over 8, because the square root of 8 times the square root of 8 is just 8. So those square roots just kind of like, bye. So square root of 5 times the square root of 8, because you're multiplying, you can use the product property that we saw up here. Where'd it go? Right here, right? Product property. You can just multiply them because they're both under the same radical. So we have square root of 40 over 8. Now, you have to check, does that 40 simplify? Okay, so we're gonna go on ahead and make our beautiful factor tree. So we have 40. Well, 40 is 2 times 20. 20 is 2 times 10, and 10 is 2 times 5. Square root means I want groups of 2, right? So I have a group of 2 right here, so I can take that 2 out, and we're gonna end up with the square root of 2 times 5, right? This is what was left over, so that stays inside. 2 and 5, I can't take them out, there's only one of each. So then we have 2 times the square root of 10. So that means that the square root of 40 is really simplified to 2 times the square root of 10 over 8. Well, here we can see that 2 over 8 simplifies to 1 over 4. So we have the square root of 10 over 4. That would be your final answer. It's really just a lot of playing with numbers at this point and simplifying once you find the rules. Okay, so let's do the next one. Again, square roots are so easy. They're the easiest, okay? All you have to do is multiply it by that denominator and then poof, done. Okay, well, not poof, done, right? Okay, so we're going to, we have 5 over square root of 5. So I'm gonna multiply both of them by the square root of 5. And again, we saw from up here what happens, right? You're gonna end up with 5 to the power of 1/2 times 5 to the power of 1/2. You add their exponents, you end up with 2 over 2. 2 over 2 is 1. So basically the square roots just cancel each other out. So you're gonna have 5 times the square root of 5 over 5, right? So these square roots end up canceling each other out. So you just have 5. So then you can see here that 5 divided by 5 is really just 1. So you have the square root of 5. 5 is a prime number, so it has no perfect square. So you're done. So 5 divided by square root of 5 is really just the square root of 5. Your homework is mostly like examples 3 and 4. So I'm gonna go on ahead and stop there for now. And on the next class, we'll get started with these last examples because these other examples are a little tricky. And on your homework, you only had 3 problems that were like this. All your other homework problems are like simplifying, which was all the other stuff. We have 8 minutes left. Do y'all want me to go back and do 9 and 10 with y'all since we're not going to do the rest of these? I feel bad for 6th period. I'll tell them to go watch the video. Okay. So because we're not going to do examples 1, 2, and 5 until the next time. So let's come back here. Example 9. So that's the square root of 216 times x to the power of 5 times y to the power of 8. Let's go on ahead. I'm gonna give you 2 minutes. Go on ahead and get that started. And then I have this 2, and then I have one group of 3 there, and then I have that 3. So that means that I'm able to take out 1, 2, and I'm able to take out a 3. So then I am left with 2 times 3 is 6, square root of whatever's left over, which was a 2 and a 3. Well, what's 2 times 3? 6. So then I have 5 x's, 1, 2, 3, 4, 5, and I have 8 y's. 1, 2, 3, 4, 5, 6, 7, 8. Now remember, I want groups of 2. So 1, 2, I have 2 groups of x's, 1, 2, 3, 4, and 4 groups of y. Okay, that means that this x is going to come out. So is this one, right? And then I have 1, 2, 3, these 4 groups, right? So that means on the outside, I'm going to have 1, 2, 3, 4 y's. Each y represents one group. So what am I left with? Well, that means this is going to simplify to 6x squared y to the power of 4 square root of 6. And I only have 1 x left over on the inside, so that x is going to go there. So this would be my simplified answer. Okay, you're going to do example 10 on your own. You have 3 minutes before the bell rings, so you should do that now so that you can have your notes. This last page, you don't have to take a picture of this one because you're going to have to take a picture of it for the next set of notes, okay? Because we didn't finish all of this. Like this lesson was way too long for one day. So we're just going to go on ahead and finish this, and then we'll do the next lesson, okay? So you only need to take pictures of 111, 112, and 113. So that's what I expect for you to submit. As for your assignment, you only need examples 3 and 4. So none of your problems are going to be harder than examples 3 and 4. So you can still do your assignment. Okay.